key. So, I've got a roof, and it's a big thing, covering a large area. And the roof itself has to be made out of something which is capable of holding up a continuous load of snow, uniformly distributed across the whole thing. So I've got some kind of panel put down. And, well, the panels are pretty small. What holds them up? Well, underneath the panels, we've got this system of trusses. On two different scales, two different ranks, working from the ground up, backwards my normal approach. There are columns. I have them equally spaced along the outside edge, the long edge. And then each column, pair of columns, holds up one truss. So that spans a great distance. I believe this particular plan is a simple 100 foot by 200 foot. So this is a fairly large 100 foot long truss. It looks like it might be about a little shallower than a 10. So each of these panels is, well, each of these panels we can tell is 12.5 feet across. And maybe 10 feet tall, maybe 8 feet tall. And there's a series of these trusses held up by the columns. And what holds up what do the trusses do? Well, the trusses hold up these smaller trusses which run the opposite direction. So two large trusses hold up a number of small trusses running across between them. And it's important to notice that the small trusses only rest on top of a joint in the large truss. Part of the definition of a truss is that the members are all axially loaded, meaning they're only in tension or compression. And if we put a truss in the middle of a member, well, then that member would have to act like a beam and it would bend. It wouldn't be axially loaded. It would be loaded from the side. And this thing wouldn't be a truss anymore, and it would be in danger of breaking. So there's a direct tie between how many of these smaller trusses I have and the spacing of the panels on my larger truss. Now, if I wanted, I could put more members in the larger truss. You don't have to load every joint. You could load every other joint and leave some blank. In this case, that would make each of my bays fairly narrow and fairly tall, which increases the angle on my diagonals, makes it kind of steep, which means it's not doing quite as much work as it could, and I end up using extra material. So this shallower angle is probably going to be more efficient. It makes the members longer, and if they're in compression, they're more likely to buckle. But, you know, structures is all about trade-offs, and we don't have the tools yet to try to finagle those trade-offs. And my smaller trusses, they hold up. Well, the distance between them is still a little too far for a single panel. Maybe we could have got 2.5 panels between them. So we run these thin members. Beg your pardon. There we go. So this is a purlin, a simple beam used to hold up roof deck. And it's drawn as a cold rolled steel, sorry, a hot rolled steel C, but that's just due to the options built into 3D Studio. Normally it would be a lightweight cold rolled steel thing. I may have put some numbers somewhere. On purlins. No, I do not. Oh, before we get to the purlins, we have to get to the things that the purlins hold up, and that's the deck. Oh, what is the deck made out of? Before we do that, you can tell us it's totally organized. I have an outline. I had it all pretty in Photoshop, and then Photoshop crashed, and I was sad. Oh, wait a minute. I think I actually think it came back up. Let's grab it. Photoshop. There it is. So here's an outline for things we need to do in order to get from our proposal all the way to a finished project. So my proposal, I said there's going to be decking. I didn't say what it was. I didn't say how big it is. And if I don't know how big it is, I don't know how far parts of purlins have to be. I don't know how far parts of purlins are. It's all cascades. So while it may look like there's this illusion of a done design, I don't know if that's right yet. Maybe it turns out that there's adjustments need to be made in terms of distances between things. So we need to actually finalize the design, and we will start with the snow. What holds up the snow? The decking. Well, my decking is tab. One of these tabs. Here we go. I just Googled for metal roof decking span to see how big a piece of metal deck I could get. Well, you can get a lot. I looked at a number of different options. There's this one here, which is hard to read, but it suggests single span. That's just your deck goes from here to here without anything in the middle. Comes in 4 different gauges, and I don't know what this number is. Oh, this is going to be the span in inches. So it goes up to 90 inches, and I should be able to do the math cool and quick in my head. That's what, 7 or 8 feet? 90 divided by 12 is 7.5 feet. And that can hold up 120 pounds per square foot. Okay, I don't think I'm going to be doing 120. We don't know yet. Ah, why isn't that on my list? We'll get back to the snow in a minute. This one suggests that for whatever their deck is, and maybe the first one was 1.5-inch simple roofing. Maybe this is deck used for composite decks with 6 inches of concrete poured on top. Who knows? But what I'm taking as a takeaway for this, we don't have the background yet to know exactly how to choose anything. So I'm just saying, okay, well, there's this stuff called metal decking, and what can it do? Well, one source suggests 7 feet. This has got a bunch of different kinds. I don't know what they are, but you can buy one that'll do 21 feet, and some which will only do barely 3 feet. So, yeah, maybe 5 to 7 feet, 6 to 7 feet. And I got one more thing pulled up. This one is 3-inch decking. And what does it offer me? Scroll down. It offers me single span, multiple gauges, looking at the middle. Well, the maximum is 15 to 18 feet. Uniform total load in pounds per square foot. 50, 60, 80. I'm only dealing with snow, and my snow is going to be somewhere between 20 and 50 probably. So, yeah, I know it kind of looks like I can maybe do a 10-foot span. And that's all I want to get out of this is just, it seems to be safe to do a 10-foot span for my decking. So, zooming in, just look at those. So between my purlins, one piece of deck, let's say it can reach 10 feet. So I've got that number locked in now, 10 feet between purlins. Then how long can a purlin be? Found another website. I asked quite simply, how long can a purlin be? I think it was that basic, right? And it said, purlins can be over 30 feet in length. I'm like, well, that sounds like a maximum or an extreme, right? Oh, can be over 30 feet. I'm like, yeah, what's normal? Maybe normal is half that, 15 feet. Here's another website. A 6-inch purlin can span 18 feet. Again, that sounds like a maximum. So I'm going to go with 15 feet. I'm going to say one purlin can be 15 feet long. So this distance is 15 feet. They're 10 feet apart, and they can be 15 feet long. And that's going to start to dictate both the configuration of any given individual small truss and the layout of the small trusses. The layout of the small trusses generates the layout of the configuration of the large trusses. So it's almost starting to come together. What do we got? Let's pull up AutoCAD, see if we can get a drawing. Let's actually do a nice job. New layer, purlin, new layer, small truss, new layer, big truss. Yeah, we'll put in the deck as well. In my mind, all deck is made out of plywood even when it's not. So the deck will be plywood colored. The purlins are cold rolled steel, so there'll be a cold steel color. The small truss will be red because they're already red. Use a more attractive red. And the large trusses will be green because they're already green. And I'm going to want a layer for my dimensions. And my dimensions are going to be cyan because all dimensions are cyan. And the first thing I want to do is start with a piece of deck. So, rectangle 0 to, how big did I say the deck was? Well, the deck is 10 foot long, but I don't know how wide it is. And then since they all just sort of line up together along the purlins, I don't care. I'll just make it 5 feet. I'm going to lay down a couple of them just to get the idea of some deck across. That's weird. I could have sworn those were rectangles. How did they get broken? Yeah, that's a rectangle. It works that time. Dimensions. It's supposed to be on dimensions. Oh, you know what? I clicked the color box. Did it again, didn't I? Yep. So if that's some deck, then there need to be some purlins. And how long did I say a purlin could be? A purlin could be 15 feet long. So there's one purlin. Okay, the deck is already starting to get in the way. Not surprised. Kind of worried that would happen. That's a lot of purlin screw. Where are you going with them? Don't know. At the end of each purlin, lays on a small truss. So there's some small trusses. Let's give them a fatter line style. Turn on line weight. There has to be something holding up that end. So we'll copy that down to there. And the small trusses are as long as the big trusses are far apart. So if that's my 200-foot dimension, 200 divided by 5, so the small trusses are 40 feet long. Feet is, nice. So that means that a big truss goes right there. And a big truss I know is 100 feet long, because I remember. And the big truss should have a bigger line weight. Lovely. And there should be another one of these every 40 feet. 1, 2, 3, 4. Yeah, the deck is 10 feet, and the purlins are 10 feet apart, so 4 of them is 40 feet. And that's more than 200 feet now. 1, 2, 3, 4, 5. It's 5 of them, right? Throw in a dimension from there to there. 200 feet. And another one there. Let's move that out a little bit. So that we can mark the truss spacing as well. Or the, truss spacing. So all I got to do now is just copy this stuff over. And, I mean, technically maybe nobody'd notice if I just stretched it all the way out. But let's be good. And small trusses go to there. Maybe 3 of them. One of the things we're going to do right now is we're going to find out if it actually all fits together. Does 15, I don't think 15 goes into 100. Does it? Divided by 100, 15. 15 goes into 100, 6 2/3 times. So, I got me a problem. I either have a funny spacing or I need to shrink something up. I need 5 feet. Make it a little longer, push it out. Well, here's a question. Copy one of these over here. Actually, we'll copy 2 of them over there. And we'll use divide. And we'll divide this one into 1, 2, 3, 4, 5, 6. We'll divide this one into 7. To turn that snap on. I have 16'8", or really now 14'3" and 55 1/28. 14'3" and a half and a buffer somewhere. Verify in field. I think we're going to go with 16'8". That's still well within the can be 30 feet long. And it's probably easiest to just delete everything and start over again with the new numbers. Why did you calculate that ahead of time? Because I'm a visually oriented person and I needed to see how things were going to behave. So these can still be 10 feet apart because nothing's changing about my deck. The deck is still deck. I just need 16'8" on my purlin length. So I'll start one over there just so it's visible. Purlin. This way, 16'8". There's one purlin, and it doesn't hold up an obvious piece of deck. Does 16'8" divide nicely by 3? 16'8". Oh, if AutoCAD will do that. 16'8" divided by 3. 0.66. That seems unlikely. Okay. Divide times 12, 16, plus 8. I did all of that by 1, 2, 3, divided by 3. 0.0 is 66.666 inches. Yeah. I think I'm going to choose not to care about the width of the deck. I'll let the people up there deal with it. And if they have to saw some in half, they have to saw some in half. And I'm going to copy a truss to there. And I'm going to copy a purlin to here. And here. And well, technically they don't really need to go there because there's a truss there and it'll rest on the truss. And I mean, technically they do because we're loading at points. But it's not going to show up in the drawing. I'm going to not put it because it doesn't show up in the drawing. I'm going to turn the deck off again. Copy this stuff here to here. This had better like fit perfect, or I'm going to be sad because math. Nice. I can get rid of those. Fix this dimension. Copy all of this stuff, but not the dim. From here to here to here. Okay. They're still 10 feet apart because the deck is still 10 feet long. 16 foot 8 divided by 16 foot 8 divided by 4 nicely, right? 4 foot 2. Yeah, it does. I don't know if they'll sell that to us. If they don't, well then we'll do something else. This to, I don't know how to do this well in AutoCAD. 4 foot 2. Yeah, it didn't work. Does that give me the same grip? 4 foot 2. Yes, that does. Oh no, it doesn't. But that was a so there. Okay. I got individual pieces of deck which fit on top of my purlins, and the purlins fit on top of the pink trusses, and the pink trusses fit on top of the green trusses. And I'm sending these back. And I should put in a deck arrow. All right, so now I know what this looks like. I know how big everything needs to be. So I want to draw a small truss. A small truss I know is going to start with one of these. I know it has to have support points. There. Now what did I draw back at proposal time? Oh wow, look at these. Those must be really close together. Sulfur tape snap. From here, this is a click and drag tool. That is 57 inches. 4 feet and change. Those are small. Well, I wanted to do a nice little cutting on the bottom, and I was doing an alternating pattern for no particular reason, because we haven't studied the different kinds of trusses and the different benefits, etc., of each of them. So if this is going to be this long, and I want to have a truss with, let's say a span to depth ratio of 12, I'll just scale this 1 over 12. I mean, we're supposed to know how long it is, right? How long is it? It's 40 feet, right? Yeah, it's 40 feet. I should put a dimension on that. So if it were 1 in 10, it would be 4 foot tall. This is 3 foot 4. That's a fine size. Look at this. Is that going to be too shallow? Where's the button for dimension angle? Creates multiple types of dimensions. Angular. Between this and this. That's 18 degrees. And that's starting to get into dangerous territory. Let's say there's 100 pounds or 100 kips, 100 units, 100 anythings. And I want to divide that by the sine. Now, if I do sine 18, I think AutoCAD thinks they mean radians. That function. Sine 18? 18, clear. 100 divided by 18 sine equals 323. So we're talking over 3 times as much. That's not too bad, but it's over 10 feet. I just don't like that. I could just make it a little taller, but then it's kind of ugly. Again, for no better reason than because we haven't studied it and I don't know, right? How about if I propose that? That looks like something we might see in the wild. It actually looks a little steeper than something we might see if we just like went into the big box store and looked up. It looks reasonable. And we're going to have loads here. I think I want 6 inches. Yeah, it's nice and chunky and ugly. That needs a new layer. And loads are green because loads are green. And this is a load. Oh, big trusses are green too. It's going to get confusing, right? Now, we were talking earlier that the purlins, are they going to rest on the big trusses because that's what they line up with, or how is this going to be constructed in terms of the vertical stacking, vertical depth? In reality, things can be done different ways, but I want to just keep this one strictly boring and hierarchical. I'm just going to say that all of the purlins transfer all of their load to a truss, to a small truss. And they're not sharing, and we're not trying to cheat the big trusses into having beams for top. No, it's just everything's pristine and pure, and no offense, kind of structures want me. To mention this, worked for a firm once, and they were like, "Thou shalt not ever write typical on anything," and I'd never heard of that before. Because like in school, we just throw down one dimension, right? 5 foot tip. And they're like, yeah, but what happens if that piece of paper gets torn off, or if there's another blank dimension somewhere and it says tip, and they're like, oh, 97 feet tip. That must mean that these are 97 feet. I'm like, no, it's those things over there that are 97 feet. Like, y'all are making sense. I think I'll actually abide by your rule not only while I work in your office, but I'm going to start doing it for the rest of my life. So there are no tips in my world, which is a good reason for why I am not a waiter. So that's what one little truss looks like. And the little trusses all sit on the big trusses. And the big trusses are ginormous. And the big trusses have little trusses every 16'8". Oh, I don't want number of segments. I wanted 16'8". 1, 2, 3, 4, 5, 6 segments. And I need to put a point here and a point here before I delete that. Let's just use the loads. Copy a load from here to here. And then it's easy to do that when you can see them, isn't it? Yeah, okay. Undo. Delete that. Move these up here. Delete that. So if this is 100 feet long, And I want to be a little conservative and maybe also just go for some of the visual drama. Let's make this one have a expanded depth of 10. Big, fat, chunky one. This doesn't work. Is that an even number? That is an even number. Good. And since these are getting big, and this is 100 feet, 100 feet divided by 6 is 16. They're almost 17 feet long. Oh, they're longer than 17. Each bay is 17 feet. Each panel is 17 feet. And these are, well, longer. Find out. There's a command for that, right? Almost 20 feet long. At 20 feet long, these things are going to want to buckle. So, if I slant them this way, they'll be in tension, and things in tension never buckle. So that is going to be a main truss. 10 foot tall, 100 foot long, with 16 foot 8 panels. And again, there's a certain degree of, maybe it won't make sense technically, but we're learning how to do it. And we're trying to keep it within a certain degree of reasonability. And again, within the confines of what we know from this class. There's my big truss. And, well, what holds up a big truss? A column. What does that connection look like? If we'd have had the time, I'd have made you think about it. But we don't really. So, getting crazy. Just want my view back. Okay, so it's going to be columns. So, how tall are they? I don't know. I'm lucky I made them out of boxes, and it still says. It's a box. Those are 720 inches tall. And, ooh, they're not square. They're 60. These are big. Well, they look cool though, right? Oh, I don't have a layer for the column. New layer, column. Columns are great because they're made out of concrete, even though this one's going to be steel. And on this one, I am adding a note. You can put a second line of text, can't you? Or make it double line? I forget. We're going to do it this way then. We'll use the forbidden explode key. There. All right. This is my roof designed, or at least configured, maybe. Visually designed, structurally prepared. I don't know what the words are going to mean there. To me, if we're talking about we designed it structurally, that means we actually said how big it is, you know, like for the members even. This truss is made out of HSS 3x3 quarters, right? Now you know what to buy. That's a structural design. A structural design should tell you what to go out and buy. And just saying, look, here's a picture of the structure. That's not a design yet. I mean, it seems more firm than a concept, but it's not a completed design. It's certainly not a completed project. Okay, so where are we on the outline? On the outline, we have, I need to save this because it's recovered. Save as, it's in the right folder. No, it's not the right folder. It's close though. No, project. Outline. Yes, I do. Thank you. See, with the fade and stuff, I couldn't do this. Well, maybe I could have done the fade in InDesign if I'd have thought harder, but I did it in Photoshop. So we have finalized the decking, the purlins, the small truss, the large trusses, the columns. We have drawn it. And drawing it not only helped us know what it looks like, but it actually was kind of like part of finalizing. You know, remember I was drawing it out and I'm like, oh look, my small trusses don't fit in my footprint perfectly. I have to change their spacing. Plan, I got 2 elevations and a column. So that's done. Determine loads. That's why I didn't do it before, because we weren't supposed to do it yet. Snow load. Well, one of the things you're supposed to do is learn how to look up a snow load by yourself. And you've been told, thou shalt build this building in Boston. So I'm going to build my building not in Boston. Boston is up there somewhere in the hard to read portion of the maps. And I'll pick Chicago. I got rid of the numbers, didn't I? Oh, no, you can still see. So Chicago is right about here. Let's make sure. I don't think it's way down there where the state line is. Googlers. Let's go for maps. I like Google Earth better because it's more fun, but you can't always get what you want. Yeah, okay, so there you go. There's Illinois. There's like a little heel up there. That's the little heel up here. So yeah, Chicago is definitely in the red circle. Sweet. So Chicago is in this barely slightly greenish light blue, which is 25 pounds per square foot. Clear all drawings. Close that down. No, do not. I want to keep the whole map. So my snow load is 25 PSF. And well, if I were good, I'd go back and I'd check the project to see if there was dead load and stuff. I'd better go back. I'd better go back. Project assignment. Ooh, roof deck material can span no more than 10 feet. Oops. I'd better go fix it then. I'm really tempted to say, well, it's the same. You can do it. You know, oh, it does span 10 feet. It's the purlins I made longer. Okay, never mind. Cool. Guess I got lucky. To support snow load for Boston for International Building Code. Use the hard to read map. Okay, that I'm cheating on purpose. There's no. I should have included a dead load. I'm going to go with something like I was in a hurry. Okay, so that's the only load. I think the deck probably weighs 2 or 3 pounds. Anything you put on top of it maybe weighs a pound or 2, unless you're making a big fancy thick roof with insulation and everything. So, okay. 25 PSF. So we need the loads on the joints of the small trusses. So each one of these loads comes from a purlin, and the purlin, let me get, I'll work on layer yellow. Oh, look at this. This truss on the outside holds up only roof here and air over here. Whereas this truss in the middle, a more typical truss, holds up roof on both sides of it. For the purposes of this project, just do the typical. I don't need to know both. I'm going to say, I want to make my outside trusses the same as my inside trusses, because when you think about it, I'm not very good at clicking that button. There we go. If this truss here on the outside were made out of slightly smaller members, well, then everything would look kind of stupid from in here. I mean, and it may depend on your project. You know, you're going to see 1, 2, 3, 4, 5, 6, 7 times 5. So it's like, I need 35 of these and 10 of these. That's actually probably economically worth doing. And it's probably not too hard to, keep them separate batches. Those ones over there go everywhere. Then that small pile, they go on the outside edges. You can probably manage to get your construction crew to put the right truss in the right location. But structure's one. I'm trying to make this a little easy on you, right? So we're just going to make them all the same. But if we're going to make them all the same, we should do the worst case. And the worst case is the truss that's got stuff on both sides. Well, on both sides of this truss, there's a purlin coming in from here. Again, bad with the clicking on buttons. And some from here. So the tributary area is going to be that. So this area becomes that load point on the truss. And that area is 10 feet by 16.8, or more carefully, 5 feet and 5 feet, and 8'4", and 8'4". And I want decimals. So 8'4", 16'8" is 16.6 bar. And 10 feet is 10 feet. $16.666666666 times 10 equals 166.6 bar square feet. So if I have 166.6 bar square feet times 25 pounds per square foot times 25 equals 4166.6 bar pounds, or 4.2 kips. Maybe if I were really doing this and somebody had to pay for it, I wouldn't round up quite so much. But I'm doing this for structures class, and I want the math to be easy and the thing not to look too cluttered. So I think I'll let you get away with 4.2 kips as a load on each of the smalls. What about the end? The ends. If this truss and this truss bringing this much area in create 4.2 kips, well, here at the end, we're only getting 1.1 kip. Sorry, 2.1 kip. Oh, I have a nice piece of text somewhere, don't I? Where did I put that? Over here. copy this. So this 4.2 kips. And 2.1 kips. Driving me nuts. Because it's multi-line and I keep thinking it's single line. All right. Now, if we were doing this a little more completely, we wouldn't know the weight of this truss yet. So the first thing we do is we'd go in and we'd solve this, and we'd find out what everything is made of and find out what that weighs, so that the weight of that truss can go into the big truss, which is holding it up. But since we're doing this on the cheap, and there is no dead load and there is no self-weight, I'm just going to find the reaction. Now this truss is supported on both ends, exists between the two supports, and is symmetrically loaded left-right. There's a 2.1 here, there's a 2.1 on the mirror side, there's a 4.2, there's a 4.2. So I can cheat. 2.1 times 2 plus 4.2 times 3 equals total load of 16.8 kips, but nobody cares, but divide that by 2, and each reaction is 8.4 kips. Well, I wonder if mirror text is on. Mirror text is not on. Good. Eight point 4. Control Enter. Yeah. So this truss pushes down at each end with 8.4 kips, and the quote ground pushes back up with 8.4 kips. But what's really going on? Where does that happen? That happens right here. This smaller red truss isn't sitting on the ground. I keep saying a reaction is the ground pushing back. This is sitting on the big truss. Big trusses aren't green, they're blue. Unless they're green. Go figure. So the reaction on the small truss is coming from the large truss. So that load, or that reaction, 8.4 kips, holding up the small truss, is also the load pushing down on the big truss. So I go to the big truss, and this 8.4 tips becomes the load. Except, let's look at that again. What's really happening at the big truss? What's really happening at the big truss? Are these on layers? That'd be cool if I were that clever. These are not well layered. I'm a bad person. What's really happening at the big truss is that there are two little trusses loading every joint. So it's not 8.4, it's 8.4 times 2. So if we look at the elevation with the little truss, there's another one right there, and they're both resting on a big truss, which we can only see end on. So there's 8.4 and 8.4. So that load is going to be 16.8. Except out here at the end, where each little truss carries air on one side. This keeps happening. You get to an edge condition, and your tributary area, half of it consists of air and half of it consists of roof. The typical connection, the typical joint, the typical truss resting on a joint. The typical truss anywhere in the roof is holding up tributary area on both sides. So all of that area, well, one end of it, right, comes down there. So the typical truss is the 16.8. But here at the ends, there's air, so it's going to be half the 16.8. So these are back to 8.4. And the big truss on the very end has got air on this side. So its typical loads would be 8.4 instead of 16.8. And its very end load, or the tributary area, is only this quarter of the typical one. This one would be 4.2. But for this project, we're not bothering with the weird ones on the edges. We're just going to take the typical one. The typical one's this one here. It's loaded from both sides. So now I know the loads on my trusses. Excellent. And while I'm here, Might as well do the reactions. Those reactions will go on the column, and those reactions will help me when I'm solving. Okay, I've got another simply supported truss that's symmetrically loaded. So I've got 16.8 times 1, 2, 3, 4, 5, 6. 16.8 times 6 equals divided by 2. 50.4 kips. So let's go look at a typical column. There's one on a corner, but corners are weird. There are no columns in the middle because we were required to keep the interior space clear. So these ones along the perimeter, these 6, 3 here, 3 over there, are the typical column, and the typical column has one big truss resting on it. Depending on how things in the world are constructed, you know, maybe this truss would go to that. I believe the load determining plan problems that we did earlier in the semester, they did have that. They look like columns with girders and beams, and then the beams on the outside, they just go straight to the column. But then you start getting into mixed up things. Well, this column's got this and the beam. We already said for this project, or at least my solution, that my big trusses have little trusses all over them. So this little truss is going onto the back big truss right at that point, which makes that connection hard. But again, structure's one, keeping it simple, keeping it simple. Wait, how does having a hard connection keep things simple? Because the location keeps it simple. The end of the truss has got a joint on it. I'll put my truss right there. The end of the truss also has a support, so I'll put the connection support right there. Everything lines up. The math turns out to be really easy. It's the detail that might get tough, and we're not doing the details. So that's cool. So if one column has one end of one large truss, this reaction is provided by the column that the truss is sitting on top of. And now I have got on the snow load, on the loads on the joints and the trusses, the loads on the joints of the large trusses, the loads on the columns. Section 3 is done. Now, all I got to do is solve the solvable bits. This is written as small truss, member forces, and member sizes. But I think I'm going to do this as solve member forces, 1, 2, then go back into member sizes and member sizes. Just sort of a, you know, a mode of analysis. What are you doing now, Groom? I'm analyzing all my member forces. What are you doing now? Now I'm sizing all my members. Again, technically that should be backwards, right? because you need to size all of these before you can even get the loads on the large truss in order to solve for the member forces and then the member sizes. So I guess I'm teaching you bad habits. Try not to hate me. That's AutoCAD. Okay. Oh, start the little truss. Which one of these has got more joints? 1, 2, 3, 4, 5, 6, 7, 8 panels. 1, 2, 3, 4, 5, 6 panels. Aha. So I want to do one graphically and one numerically, method of joints. So I'm going to do the one with fewer joints, the big one, method of joints. And I'm going to do the small one by graphical. So let's pull this over here. And graphical method. First step, find the reactions. Done. Next step, Bose notation. So I want to put it there. I want to make it about that big. I want it rotated 0. And it's a capital A, the other kind of capital A. There we go. Copy. Oh, you know what I want to do first? I just want to make this justify middle center. Do I need the dimensions for anything? I'll keep them. I'll turn them off. I'll keep them, turn them off for now. B, C, D, E, F. Okay, if I do 1 inch equal 1 kip, because that's the easiest to draw, it's fairly small. I have two choices. I can either scale this down or I can split the views. Do I remember how to split views? Views, viewport configuration. Nope. 2 vertical. That'll work. Oh, hey, I need numbers. One. Copy this. Give me a sec. I have to check the time. I have a student at some point, and I have to make dinner at some point. And I don't know when now is. It's 1 o'clock in the afternoon. I don't think it's dinner time yet. Student is at 2. Well, we should be able to get this graphic done before the student. 2, 3, 4, 5, 7, 8, 12, 13, 14. Yuck. That means what? 4 minutes per point. Still think we can do it. Okay. Line. Down 2.1. And zoom in until that's nice. Copy this from here to here. Tail last one. That's close. I turned snap on. I did. One again. 2. 5. Good enough. And I do want a little tick mark there, just to make it easy to see. B. From B to C is down 4.2. And then D to E, C to D, D to E, D, E, F. Before I forget, F is only halfway. F, E, and then from F up 8.4 to G. 8.4. There's G. G. Very tiny, very large. So, from A to anything, there are no actual member forces of the truss next to A. This space here, that belongs to G. Let's scribble over that for a minute. The space between the forces is the space between the 8.4, all of these members, even this member, and that 8.4. This whole space is G. B is the space between that load and these two and that one. And A is next to that force. And yes, it touches the tippy end of those two members, but that's just a joint. It's not a member. There's no force that's an edge of A. We go from the 2.1 load immediately to the 8.4 load. So this space A, it doesn't have anything to do with our truss. And that's because these two forces are kind of in the same place, and they just shove the truss off to the other side or something. Doesn't matter. I mean, it's not like, oh, what will we do now? Well, what are we trying to do? We're trying to find point 1. And point 1 is between B and, or point 1 has this member between point 1 and B, that's horizontal. So I'll draw a horizontal from B. And point 1 also shares this member with G. What is that angle? Don't know. I can set AutoCAD up to let me draw on it. What's that angle? Dimension, angular, this and this. Is it really 34 degrees? Or is it something fancy? I bet it's fancy. And that's just rounding error. No, the measurement is actually 34 degrees. Edit dim style. Modify. Primary units, angular precision. Yes, it's 33.69 degrees. Okay. So we'll go into ISO mode. I thought it was ISO mode I wanted. No, it's the specific angle mode I want. There it is, tracking settings. Polar tracking. I don't want polar tracking. Snapping rate, angle settings. I did this the other day, but I did it with like 30/60, so it was easy, right? Yeah, tracking settings. It's not tracking I want. Polar tracking on. Angle settings. Additional angles. This is it. New. 33.69. New. Negative 33.69. Okay. But I should do the jump. So between G and 1 is a point on this angle. No. That's the 30. I don't want your 30. I just want the additional angles. Well, give me the additional angles. That's because it's not on there. Now it's on. Don't want the 150. Don't want the 180. Don't want 210. There's something wrong here. I'm going to do it with just copying the lines if I have to. Additional angles, equal angles. 90. Because I keep that out of my space. Give me the additionals. 34 and 326. That should totally work. Right? Right. Line from G. Hey, I quit. Here to here. The G. So, it's extra long, but it does the job. Where these two lines meet, that must be point 1. Between 1 and 2 is a vertical line. And between B and 2 is a horizontal line. Oh, this must be point 2. And it is. If you look at this, well, there's only one vertical force at this joint. And if there's only one vertical force, there's nothing to counter it. So that force has to be 0. It's a concept we haven't looked at called zero force members. It's something most structures classes make you learn how to find the zero force members in this truss, and then they never do anything with it. So why does this exist? Well, it exists to give me a place to, just sort of mark where that joint is. But well, what if we delete it? Because we don't need it. Well, that makes these long members on top, which are in compression, twice as long. And if they're twice as long, that makes them 4 times as weak under buckling. So these members here, they don't carry any load, but they prevent the top from buckling. Well, what about the bottom where it's in tension? It looks good. We could delete those. Truss would look funny, and we'd have longer members. And one of the nice things about a truss is that it's made up of short members. So that's point 2. Between point 2 and point 3 is a line at this angle going the other way, like that. And then 3 shares a force on that member with G. That member is horizontal. Whoa, look at that. We're kicking way out. So this force got big. Or did it? Compare to 1 to 2. Or, oh yeah, no, there is no A, right? So, yeah. G to 1. It looks like it's actually the same as G to 1. I feel like that doesn't make sense. No, G to 3 is big. 2 to 3 and 1 to 2. Yeah, okay, those are good. Stop thinking. Do more drawing. 3 to 4 is a vertical. And 4 to G is a horizontal. So yeah, we're getting all these 0 members. Oh. Yeah, I'd redesign the truss. There are no requirements for how it looks or how efficient it is or design it for the best cost. So I'm just going to keep drawing. 4 to 8 is a copy of this one. And C to 8 is horizontal. C to 8, definitely C to 8. And, 8 to 6. How did they get numbered like that? 1, 2, 3, 4. That's a 5. 6, 7, 8, 9, 10, 11. That's a 5. 5, 6, 7, 8, 9, 10. Yeah, the rest of it I think is cool. Math is hard. So 5 and 6 are going to be in the same place because this member is also going to be a zero force member. So I've made an interesting trust, 5, 6. And 6 to 7 is, did I screw up? I screwed up. The line between 4 and 5 is this one. This is one of the reasons I do colors when I start. Makes it a little easier to see what you're doing and to not screw up. The line from G is horizontal, but the line from 4 to 3 is the one that goes up to the left. Sorry, from 4 to 5. That angle. This angle. That is 0.56. 0.586. 0.56. 6 to 7 is a copy of this. And 7 to G is a horizontal, so 7's out here. And 7 and 8 are separated by a zero force member. 7, 8. 8 and 9 are separated by a down to the right. So it's going to look like that. 8 is next to G. I got that. 9. 9 is adjacent to D on a horizontal. Get my horizontal out from D. And so this horizontal and that diagonal cross here. So this is 9, and 10 is also the same because zero force member. 10 to 11 is up to the right. Oh, there's a line there already. I'll copy paste it. There it goes. And 11 to G is a horizontal. So G is this one in the middle. So this point is doing real multiple duty for me today. It's also 11 and 11 and 12 are separated by a zero force member. 12. 12 to 13 is this diagonal. 13 is horizontal from E. There's E. So 12 on that diagonal, 13. Thirteen and 14 are separated by a zero force member, so they're in the same place. And that's point 14. It's done. Now I just have to measure everything. version with Bose notation is too messy. So I'm going to make a version down here without. And copy this. And that's compressible. How about if we do it this way? Great. X execute. And scale that by half. Again. Hmm, 1.5. That'll be crowded but legible. There and there. Just setting myself up for the labels. Don't need those. I know those are all zeros. What's the zero look like? Capital O looks better. I'll use that. All these zero force members, I feel like I'm wasting money, but I got to remember that at least the compression side's important. Told you. Crowded but legible. Wicked crowded. All right. So, and if I put this one, let's go to the middle. A little hard to find. Get it? Got it. Mirror, it's easier. Okay. Now I got every place I can put stuff. And if I come in here and I do need my Bose notation, so I can, that makes me sad. So I can identify the members. But we'll delete it later. Now it's just wicked messy. Well, I don't know. We'll decide later. So I want to find out the force in the member between B and 1. So dimension it, and I think I'm going to hate my dimensions. L, and I get 9 and 5/16. I would much rather have that in decimal, please. Between B and 1 is 9.34. 9.34 kips. Between C and 5 is 21.8 kips. 8. Between D and 9 I was looking at G. D and 9 is going to be 21.8. And E to 13 is going to be the same as B1, 9.34. From 1 to 3, or which number is that? Actually, that is 2 to 3. 2 to 3. Oh, look at that. A little bit of error. Oh, no. I don't think I used that line for anything, so it's okay. 11.27. 7. Did I do 1 to G? Didn't do 1 to G. 1 to G. 11.27. 11.27. 3 to G. 18.68. 8. 7 to G. Where'd 7 go? There it is. 24.9 kips. 11 to G is going to be the exact same point as 3 to G, so that is going to be 18.68. Yeah, let's confirm, right? Just in case we made a mistake somewhere. 18.68 kips. $14 to G. Nobody drew the line because we didn't have to, but we should have, or could have at least. So let's grab a copy of this, put it on G, and oh, nice. No obvious error. That always makes me happy. 11.6, 11.27. Hey, it's the same. 0.27 kips. And now we just have to do the character of everything. Oh, I missed my diagonals. 4 to 5. 4 to 5 is 3.76. 7, going to be the same, 3.76. 9, 10, 8, 9, beg your pardon. Looks like it's going to be 3.76. And 11. 0.76 kips. Why are they all the same? Well, not going to be quite the same. 4, 5 here is going to be in tension, and 6, 7 is going to be in compression. But since this is center member is a zero force member, these two have to have the same but equal, one going up, one going down. And if they're at the same angle and they have the same vertical component, they're going to have the same total force. So they're both 3.76. And then we get to the middle of the truss. And this truss is boring and symmetrical. So the two members that mirror those are going to be the same. Again, one will be in tension, one will be in compression. But that same number will carry across. Here we had the mirror image around a zero force, so they're the same. But then there's a load, so some of this 11 bled off into the 4, leaving only 3 to run to the middle. And then if there were more, it would have gone down even more, but we're past the middle, so we start going the other way. 12 to 13, probably going to be 11.27. 11.23. Somewhere there's a mistake, and I wonder if it's just in my ability to read numbers. That is a definitely not. There we go. It was just, I don't know how to use the LN tool. 11.27. 11.27 kips. Okay, character. I think that's all my numbers filled in. All right. I think we're going to use the sketch tool. Sketch. What? Red pen. So if I want to do B1, it's going that way, which is from B to 1. So I come down here and I draw an arrow from B to 1. I bring that up here. And that's pushing, so that is compression. And since this is a zero force member, I know that the one on the other side has to be the same. If I want to do between 1 and G, that's from 1 to G. 1 to G is like that. Which is pulling. So this is tension. The zero force is a zero force. The compression across the useless joint is compression. Here's 2 to 3. Tolerance 0.05. I don't know if that's what that means. We'll find out. Catch. Tolerance is an L. 0.0. We'll do try 0.05. See how that goes. I don't think that's what tolerance meant. Catch. Increment. 0.05. Clearly, I don't know how to use the sketch tool. Oh well, no worries. Catch from 2 to 3 is that way, and that is from 2 to 3. So a line arrow from 2 to 3 looks like that, sort of. Copied back here. Is compression. 3 to 4 is a 0 force. The bottom. Go around this way. That gets us 3 to G. 3 to G is like that. Copy that to here. That's tension. And I'm happy because I want my bottom, or I expect my bottom chord to be in tension. That's a 0 force member, so I'm going to copy this just straight over here. Mirror it straight over there. Over that member. Whoa, it just got better. I'm tripping. That is from 4 to 5. 4 to 5 is there. I guess you just have to wait a while for it to catch on, right? And that is tension. And that's a 0 force member. Here we go 6 to 7. Where's 6? There's 6. There's 7. That is pushing. That is compression. And this is that way. That's 5 to C. That's that way. Copy that to here. That is pushing. That's compression. Very crowded and messy. And that's the middle of the truss. And this truss is symmetrical, so I'm a cheat. Compression. The diagonal changed direction, so you might think we were tension, but we crossed the middle of the truss, so that's probably going to be compression. That's going to be tension. Tension. I hope I'm right, because, you know, like, if I cheated and I'm not right, I'm, like, going to be sad. Maybe teacher won't notice. I'm going to have to go down just 200. So there is a truss with all of the member forces calculated, both magnitudes and what are those other things called? Characters. I want to viewport configuration, single. Okay, this is definitely symmetrical. So the left hand and the right hand should be mirrors of each other. I got tension, tension, compression, tension, compression, compression, tension, compression. I got compression all along the top. I got tension all on the bottom. This is a simply supported truss loaded at or between the supports. So the entire top cord should be in compression. The entire bottom cord should be in tension. The top and bottom cord force magnitude should increase towards the middle. 21 is bigger than 9. 24 is bigger than 18 is bigger than 11. The web should decrease towards the middle. 3 is smaller than 11. So all of my rules of thumb check out. I feel like I did a nice job drawing it. I'm going to say the small truss is solved. And now I just have to do the big truss, which I promised to do method of joints. Copy. Continue. Oh, those are slightly different colors of pink. Invert, delete. Change the color. Make it green. I thought I saw green in there. There's green. Honkin saturation, darker. This layer only. That makes it kind of ugly, doesn't it? Let's colorize. What? Oh, wrong layer. There we go. Merge. Okay, the truss is good. The loads are hard to see. 16.8 and 8.4. Memorize that for me. 16.8 and 8.4. 16.8 and 8.4. 16.8 and 8.4. That's a bad 8. That'll do. Bet your J doesn't work. Could not use. Could not use. Ah, come on. There's plenty of them. 0.4 kip. 0.4 kip. We need dimensions. Should have left them on. Dims. No, nothing. Color change. Turn them on. 16, 8, and 10. (16'8) and 10 foot. All right. First, I want to find the angle. Theta equals inverse tangent of 10 over 16'8" is 16.6 bar. That angle I calculated earlier, I don't remember which one I calculated. Equals inverse tangent 30.96 degrees equals 30.96 degrees. That's going to be annoying to type all the time. Clear memory, add to memory. Sine. Sine of that angle is 0.514. Cosine of that angle is, recall memory, cosine 0.857. Okay, need labels. Joint A, B, C, D, E, F, G, H. This is symmetrical. Oh, I should go all the way. I'll do a section cut. Just don't want to do that much math. That's all. I'm just being lazy. Oh well. H, I, J, K, L, M, N. It's 2 o'clock, student at 2. I have to, pause recording, I guess. And break for student is over. Should be back recording. Solve this method of joint. I think one of these was already set up. There it is. Got my calculator out in scientific mode. And the hiccups. Joint A. It's very small. Joint A has 50.4 kips going up from the reaction. Has AB coming down, and AC, which is going to be 0 by the look of it. Sum of the forces in the x direction equals 0, equals AC, 0. Sum of the forces in the y direction equals 0, equals 50.4 kips minus AB equals 50.4 kips. 50.4. I think I'm going to skip the kips just because I don't have enough room and it's hard to write sideways. That is pointing down, that is compression. Joint B. Looks like I need 2 windows for this. Windows. Arrange. New window for untitled 1. That can go over there. That one can close. That one can close. That one is boring. And I want 2 up. Horizontal. He has 8.4 kips down, 50.4 kips up. Unknown in diagonal, that's going to be tension. The other kind of tension, the one that looks like that. Compression up here. That is BD, this is BC. Sum of the forces in the y direction equals 0, equals minus 8.4 minus BC sine theta plus 50.4 BC equals 50.4 minus 8.4 equals divided by 0.514 equals 81. And this is going to get bigger towards the middle? Holy Toledo. 81 point, no, that was BC. That's going to get smaller towards the middle. 81.7. That's pulling, that's in tension. That's a mistake. And I want these where I can see them. EC equals 81.71. Sum of the forces in the x direction equals 0, equals minus BD plus 81.71 cos theta, that is 0.857. BD equals previous answer times 0.857. 70.03 kips. That's moving on again. Compression. C. 0. C, E. C, D. That's going to be compression. 70. Nope. 81.71. Sum of the forces in the x direction equals 0 equals 81.71. That's minus, going to the left, plus CE, CE, sorry, times cosine theta, 0.857. CE is going to equal 70.03. This pattern where there's a parallelogram and the top equals the bottom, that shows up a lot. This is going to probably be, should be bigger, let's say, 1, 2, 3. Then same parallelogram rule. EG, we'll look for it to be the same as DF. No promises, but probably. That's pulling, that's intention. Sum of the forces in the y direction equals 0 equals 81.71 kips times sine of theta, that is 0.514 plus the D, y direction, CD. CD equals 50.4. You'll see that pattern a lot. Oh no, it's not going to be. I have to do math. Oh, battery. Let's hope we can get through this. 81.71 times 0.514 equals 41.999. 42. 42 kips. 50.4 minus 8.4, 42. E. 16.8. Compression 70.03. Compression D. F. Sorry for my handwriting. My tablet is dead. It's the connector where the plug fits in. But yeah, no, I don't want to work anymore. I'm like, I wish you would. And it's like, I wish I wouldn't. CD was compression. $42 kips. I've got one unknown y. Sum of the forces in the y direction equals 0 equals minus 16.8 plus 42 minus DE y direction times the sine of theta 0.514. DE equals 8 negative Oh, plus 42. I was doing that one. Okay. 0 minus 16.8 plus 42 equals 25 point. That makes sense. Divided by 0.514 equals 49.03. DE 49.03 intention. Not making it better. Sum of the forces in the x direction equals 0 equals 70.03 minus df plus dE 49.03 times cosine of theta 0.857. Why is it the eighths? df equals 70.03 plus, yeah, it's going to be plus because it's getting bigger, plus 49.03. That's spooky. Times 0.857. df equals 112.05. 112.05. That's in compression. E. I don't remember one. 70.03 EG 49.03 EF. Some of the forces are doesn't matter. Y direction equals 0 equals 49.03 sine theta times 0.514. Oh, tension better be compression. Minus EF equals 49.03 times 0.514 equals half of 50 is 25. Okay, that makes sense. 25.2. 25.2. Drawn in compression, positive answer. Sum of the forces in the x direction equals 0 equals minus 70.03 minus 49.03 times cosine of theta plus EG. Much as I like Q, this one's a G. EG equals, they're getting bigger because we're getting towards the middle. .03 minus 49.03 times 0.857 equals most of 50, so say 30, and 70 is 100, and I rounded badly. EG equals 112.05. Playing its intention, 112.05. 112.05. Get that decimal and you can see it. Tension. Has 16.8 kip coming down. 112.5. FH. 25.2. I'll move that over. FG. Fabulous gangster. Some of the fabuluses in the y direction equals 0 equals minus 16.8 plus 25.2. Those are going to sort of cancel each other out. So FG is going to keep getting smaller, and it's a web member going towards the middle, and that should make it smaller. Y direction minus FG times sine theta, 0.514. Close paren. FG equals 16.8 negative, 16.8 negative, plus 25.2 equals, divide by 0.514 equals 16.34. 16.34 drawn in tension. So the forces in the x direction equals 0 equal 112.05 plus 16.3 for cosine theta 0.857 minus FH. Putting your H's where they happen to be. FH equals 112.05 plus a small amount, 16.34 times 0.857. 112 and 10, 120 equals 126. 126.05. 126.05 drawn in compression. Now normally you'd be, well, okay, we went A, B, C, D, E, F, so the next one would be G. But I ain't no spring chicken. You ain't gonna fool me with that. I know that if I do G, I'm gonna have 2 vertical unknowns and 2 horizontal unknowns. So I ain't gonna be able to do G. Or you can look at it as 1, 2, 3, just total unknowns. Still not going to be able to do that. It happens when you get to where the diagonal splits sometimes. You end up doing the sawtooth. Up, down, up, down, up, up again. So I'm going straight on to H. I'm going to put my H where it ought to be. Not that I'm huffy. 16.8 kips down. 126.05 in, another 126.05 in, but we don't know that yet. HJ and GH. So the forces in the y direction equals 0 equals minus 16.8 plus GH GH equals 16.8. Drawn in compression. Sum of the forces in the X equals 0 equals, let's draw 126.05 minus HJ. HJ equals 126.05. Told you so. 126.05 compression. If we're lucky, everything from here on out should look really familiar. E, G. Tension, tension. That was compression, right? Tension, tension. And so all the left-right tensions should balance out. The two up tensions should be balanced by the pushing down tension. 16.34. And there's no strange angles. This whole thing should be symmetric and balance out nicely. 112.05. This is GJ. That sounds like a nickname. Yo, GJ, come on over, bring the stuff. We'll build it this evening. GI, that should be a medical thing. Some of the forces in the Y direction equals 0 equals 16.34 sine theta times 0.514 minus 16.8 plus GJ times 0.514 GJ equals 16.34 times 0.0514 minus 16.8 divided by 0.514 equals, yeah, I screwed that up somehow. What did I do wrong? 16 times a half is 8, minus 16 is minus 8, divided by a half is 16. Yeah, something was wrong. 16.34 times 0.514 minus 16.8 equals, divided by 0.514 equals 16.34. 16.34. That's the tension. So the forces in the X direction equals 0 equals minus 112.05 minus 16.34 times cosine of theta plus GJ 16.34 times cosine of theta plus GI equals minus this plus this, cancel out. Minus, that's a minus, they both turn plus, 112.05. Don't get excited yet. This doesn't mean everything's symmetrical, because this is obviously just a symmetrical joint. So it's a setup still. Not until we get a little further along are we going to be able to comfortably say, it's working out. Need to plug my phone in. Just unplugged something else. I hope it wasn't important. If I were clever, I would have paused recording. Not clever. Look it up, G. Yeah, both of them did. What comes after G? J. $16.8 kip down. Compression 126.5. Tension 16.34. Unknown, probably compression. Unknown, quite probably compression. That is JL. Double angle is JI. Sum of the forces in the y direction equals 0 equals minus 16.8 minus 16.34 times the sine of theta plus JI equals 16.8 minus 16.34 times 0.514 equals JI equals 25.2. Sweet. That's in compression. Sum of the forces in the x equals 0 equals 126.05 minus double angle minus 16.34 times cosine theta. L equals 126.05 minus 16.34 times 0.857 equals 112.05. Barely, but we made it. 112.05. That's this one. No. J. Top. 115. 2.05. A whole lot more. I. Tension, tension, compression, diagonal, tension. This is 25.2. This is 112.5. Sum of the forces in the y direction equals 0 equals minus 25.2 plus IL IK inverse kinematics plus IL sine theta. He's starting to get punchy. L equals 25.2 divided by 0.514, 49.03. I think now we can actually start to say it's panning out. And we're stoked. Tension. So the forces in the x direction equals 0 equals minus 112.05 plus IK plus 49.03 times the cosine of theta, 0.857. IK be equals to 112.05 minus 49.03, 112.05 minus plus 49.03, 112.05 negative plus 49.03, 112.05 negative plus 49.03 times 0.857 equals, I hate these phones, 70.03. 70.03. That's in tension. Okay. No, L. And 112.05. 16.8. Okay. .3. That'll be compression. That is Ln. That's sort of my mother's name. And the y equals 0 equals minus 16.8 minus 49.03 plus, okay. Oh, times sine of theta 0.514. LK equals 16.8 negative minus 49.03 times 0.514 equals 42.00142. 42. And compression. Sum of the forces in the x direction equals 0 equals 112.05 minus ln minus 49.03 cos theta ln equals 112.05 minus 49.03 times 0.857 equals 70.03. 70.03 ln up there, 70.03. Pushing compression. The 12. That was JL. JL was done compression. Throat's getting rough. After L, K. .03, 43, KN, KM. Sum of the forces in the y direction equals 0, equals, that is compression, this is tension, this is tension, this is tension. Minus 42 plus Kn sine theta times 0.514. Kn equals 42 divided by 0.514 equals 81.71. 1.71. Pulling tension. Sum of the forces, the x equals 0 equals minus 70.03 plus 81.71 cos theta plus Km. M. I'm mathing here, sorry. I'm burning out. Km equals 70.03 negative plus 81.71 times 0.857 equals 0.00453. 0. N. 8.4, 70.03 compression, 81.71 tension, and backing for compression, and M. Alrighty. Sum of the forces in the y direction equals 0 equals minus 8.4 plus NM NM minus 81.71 sine theta NM equals 8.4 negative minus 81.71 times 0.514 equals 50.398, 50.34. Not 34. 398 is 4. Alrighty. Well, you can do it visually, but, well, I'm a big fan of doing it for real. M. 50 point. Well, you can't always do it visually. Sometimes, like, there's a diagonal coming in and you've got to do some trig on it. Oh, and M was on pushing, so that's compression. So that's compression. That's, well, it's neither because it's 0. Sum of the forces in the y direction equals 0 equals minus 50.4 plus 50.40 equals 0. Sum of the forces in the x direction equals 0 equals 0. 0 equals 0 in the x, and 0 equals 0 in the y. That was happy. So, I have solved for all of the forces in the large truss. And did I save? I might have closed down the... Oh, there it is. Actually, let's see if we can get rid of the extra window now. Don't need it. And arrange one up. I did number forces, I did number size, I did number forces, and I did number size. So I solved most of the solvable bits, and all I have to do is a column. No, I didn't do member size. Why do you people listen to me? I solved member forces. Now I have to do member size. Oh, what I like about this is that I can see all my answers in one place, and I can figure out which ones I want to look at. We'll leave in order, though. Let's go back into the small truss in AutoCAD. Yeah, the Photoshop commands don't work in AutoCAD. I get answers. Here's the answers. Okay, grab this. And Photoshop, and we'll get a new drawing for this one. What am I doing for time? Not even 5 o'clock. 8. Or not that one. That one. Change the colors. 180-degree shift. More saturation. Darker. This layer only. Yuck. Maybe switch that to multiply. Multiply's my best. And we'll make another one. There. 3 of them stacked. Yeah, it's a spot healing. There we go. Okay, you're going to just touch it up by hand. There, now it's beautiful. Okay. If you want it to be really fancy, you could do every single member differently. That's a lot of work, and I'm not going to make you do it. If you wanted to be kind of fancy, you might do the top and bottom chord differently than the web members. And you see that a lot, and it makes some sense. And I got 24 in tension, I got 21 in compression, and on the web I've only got 11 in compression. So I think I might do top and bottom chord the same and web members differently. So give me a color I like. So for the chords, now we need to do stress. Worst case is for stress, well, stress is just F equal P over A. It's the biggest force. So in the top and bottom chord, for stress, my biggest force is 24.9 kips. For buckling, my worst is, that one can be a little dodgy. Well, no, I'm doing chords, so it's just going to be all the members are the same length, so I don't have to worry about the diagonals being a different length. So my worst force is 21.8 kips. And it is, that's the distance between the purlins, which is the length of the deck, and that's 10 feet. I'm going to go back and check. Oh, right, because I put in the doubles. Good thing I checked. 5 feet. 5 feet. Oh, chords. F equals P over A. Normally there'd be a safety factor, but we haven't done any safety factor stuff this semester. Do we know? what we need to know about steel. No, because nobody said what materials you have to use. I know at least one student is doing timber. I'm doing steel. So we'll just, I'm going to be taking them off the AISC chart. And so that material is all 50 KSI. And like I said, we'll skip the safeties, we'll skip the number we should use. The actual named official stress this is 50 KSI steel. And the force we have is stress worst 24.9 kips. We're looking for the area. The area equals 24.9 divided by 50, 0.498 square inches. So that's the area required not to fail under stress. My worst case top or bottom chord member. And buckling, P critical, equals pi squared big E big I over KL squared. Biggest force buckling, 21.8 kips, equals pi squared big E for steel is 29,000 KSI. Big I is what I'm solving for. K for a truss member is 1 because trusses are pinned both ends. L is, I wrote it down, 5 feet. But we want to convert that to inches times 12, so that's feet. That's inches per foot. My feet cancel out, gives me inches squared. I equals, I should use the cheat toy, but it's over there on a different shelf. 21.8 divided by pi squared divided by 29,123 times, paren, 5 times 12, close paren, squared, equals, very, very tiny number. And like 21 kips is a lot, but 5 feet is pretty short, 0.27. I'll tell you this, I did really well doing that method of joints, and I'm pretty happy with myself. But I'm going to go double check. I'll go get the cheaty toy. I was working with a student earlier today building a truss, and well, whatever. No, it was a column. No, it was a truss. And it was yesterday. And his required moment of inertia was horrifically small. Kitty toy. 21.8 equals pi squared 29,000 question mark divided by paren 5 times 12 close paren squared. 0.27 inches to the fourth. I'm going to just keep going, and then once I've got all the members, then I'll just go look at the table. And I'm running out of counter space. So, web, stress, eleven is the biggest force, 11.27 kips, and buckling, all the diagonals are the same length, all the verticals are 0, 11.27 kips, and I don't know what that length is. I could math it up, or I could just ask AutoCAD. 72.1 inches. 72.11 inch. F equals P over A, 50 KSI equals 11.27 over A, area required equals 11.27 divided by 50. No, 0.7. 0.7. TD toy is really annoying sometimes. 0.23 square inches. Buckling. 11.27 equals pi squared 29,000 big I over K is 1 again. I'm just going to not write it. 72.11 squared. I required equals 1.27 equals pi squared 29,123 question mark divided by 72.11 squared. No, 0.27. Why does it hate me? No. Times question mark. I equals 0.15 inches to the fourth. Ah, nope, mistake. Zero point 0.2 inches to the fourth. And there you go, less force, almost half. 11 kips versus 21 kips, almost 22 kips. But this is only 72 inches, or is as much as 72 inches, and that is 60 inches. So it gets a little bit longer, but it has to be up butt. Less force, but longer, therefore closer required stiffness because of the length. Not the best illustration, I didn't make it up for that. Okay, now we can do the stuff. Looking for the AISC shapes database. These are all really small. I think they're going to be double angles, so if they're going to be double angles, yeah, we'll just look at the big one. Look at the real one. Look at the real one. brave. The second tab, I don't need the fancy nomenclature. I need the area. There we go. I don't need ZS or R. Don't need ZS or R. Did I screw up? No, I got X, I, X, and I, Y. What did it do? Oh, those are... Okay, got it. Oh, it's not going to be a W44. Not surprised. I'm going to go with double angles because I like the way they can be put together with the little plates between the gap and the bolt. So, for the top and bottom chord, I need an area of just under a half. So there's area. And the smallest double angle I can get is huge. And they just get bigger. Well, not quite bigger. They get bigger and a little smaller and a little bigger and a little smaller. Whoa, what's this? I always thought there were two sections. Yeah, the LLBBs and the not LLBBs. I forgot what. No, it's long leg back to back. So double L 2 by 2 by 1/8 by 3/4. I don't need 3/4. This is this nomenclature. I can do this. So put Photoshop over there. A double angle like this with this nomenclature tells me that it's, I can never actually remember if it's 2 or 2. So it's 2 by 2, and then the thickness is the third number. So this is just a 2 by 2 by 8. And if there's a fourth number, 2 by 2 by 8 by 3/4, that's the gap between them. And the gap between them is a nice place to put a steel plate that you can bolt to. But I'm not going to need a 3/4 for this. I mean, yeah, it'll be skinny. So how about the 2 by 2 by 8 by 3/8? Well, they're the same angles, so my area is the same. It's bigger than a half, but we'll use it. So let me write that down. Different color. Therefore, I propose using a 2L 2 by 2 by 8. I wonder offhand if they don't repeat it, if they're touching or if there's a gap. I'd have to look that up. We'll just go with the 3/8 then. Because I want a gap by 3/8. A equals 0.982. Big enough. For moment of inertia in the weak direction, because this is a member in compression, so it will fail in the weak direction. The weak direction is typically Y, but sometimes they mess with your head. What can we find for an IY? Well, I need 0.27, and that's too big. And I can't get a smaller 2 by 2 than this. Oh, are those all square? Those legs are the same size? 2.5 by 2.5, 4 by 4. Yeah, those are all the same size. Okay. So these are, one leg is longer than the other, and it's long leg back to back. So long leg back to back, as opposed to short legs back to back. And that's down here, SLBB, the short leg back to backs. I don't really want a long leg or this will get fancier than we want to get into, because the neutral axis is kind of there, so it's not square in terms of x and y. You can see 1.9, 1.8, 1.7, 2.6. They're not the same, but let's just pretend we'll stick with the squares. I mean, maybe if we did a long leg back to back, where the long leg was only a little longer, we'd be able to get closer to a square. Yeah, it might actually be worth the effort. I don't want you to have to go through all that. We'll just stick with the easy ones to write down. And we'll just use a double angle, 2 by 2 by 8. And we'll stick with the 3/8 again. So we've got a place to put a plate. That's with an I of, let's see, where did I put it? 2 by 3/8. The smaller one is IX at 0.378, which is close to 0.2. 0.378. So that is, well, it's the same unit. It's big enough for both. Therefore, use double angle 2 by 2 by 8 with a 3/8 gap. It's a little overbuilt, but we can't buy anything smaller. Well, we could get a single angle. But for the top and bottom chord, I think what it is in my experience, when I look up at a store, I'm usually seeing the top and bottom chord being a double angle off into the distance. So my inclination is to use the double angle. Now let's find out what happens in the web. Running out of space. Almost done though. Perfect. Okie doke. The web is smaller. Well, we could try single angles. What's a 2 by 2 by 8 give us? It gives us 0.49 for area, and lowest is, a little bit too small. 0.27, 0.27. How are they equal? Oh, I know how they're equal. Never mind. 2 by 2 by 3/16. So for this, we could use a single angle 2 by 2 by 8 with an area of 0.491. But for this, we need to go up one shot. L 2 by 2 by 3/16 with an I of 0.271, 0.271, and an area of 0.722, almost twice as much, because it's 3 times as thick. Okay, that makes sense. 722 inches to the 4th, inches squared. This is bigger than that, and this is bigger than that, so that should be good. Therefore, use this. So those are the sizes for my small truss. Number sizes, large truss. Same endeavor. So what am I looking at? I'm looking at nothing bigger than 81 on the web. And yes, the biggest one in the web is 81. And the smallest one on the cords is 70. So these two are close to each other, but they're kind of like, okay, top cord, or the cords cover this much force between 70 and 126, and the bottom cord covers this much force between 16 and 81. Not cord, but so I think maybe I'll buy something big for the top and bottom for the cords, and something small for the web. So cords, web. Worst case cord, 126, and that's also in compression. And all of my cord lengths are the same, 126.05 kips. And it is 16.6 feet. Nice. 16.6 bar feet. And my webs are, worst case, 81. They're all in tension. But my verticals are in compression. So, worst case for stress, 81.71 kips. Worst case for buckling is compression, 42 kips. And that is 10 feet long. 50.4 kips. Double check. Cords, top cord, gets bigger, 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 126. 112. 126 is bigger. That is in compression, so we're going to have to check that for buckling, 16.6 feet. Yep. Web. Biggest force in the web is the 81. Biggest force in the web in buckling, in compression, is 50. Okay, that's still tension. I don't have to worry about it. Not going to buckle. So 50, and it's a vertical member, 10 foot long. Better hurry, finish this up before I have any voice left. Member sizes. Oh, we got to do the math first, right? Rats. Chord. F equals P over A. 50 KSI equals maximum force 126.05, because it's going to make a difference, right? Kips over area. Area for stress equals clear 126.05 divided by 50 equals 2.5. That makes sense. 2.52 square inches. I'm going to leave some space. Be critical equals pi squared, big E, big I, over KL squared. This is still a truss, so K equals 1, so I'm not going to bother writing it down anymore because I'm a slacker. 126.05 kips equals pi squared 29 1 3 variable over L 16.6. Oh, I stopped writing units. I'm sorry, I'm bad. And this is why you remember to write them. Feet times 12 inches per foot, cancel out, squared. Okay. 16.666666 times 12 equals squared times 126.05 divided by pi squared divided by 29.123. I equals 17.62 inches to the fourth. I'm going to try that on the other one, just to make sure I didn't mess up. Aren't you confident? No. I've seen too many mistakes on this equation. And deflection, too, is equally as annoying. You'll have fun in structures, too, with the deflection equations. 6.05 equals pi squared 29.123 times question mark divided by 16.666 times 12 closed paren squared. Question mark equals 17.62. Nice. So that's for the chord. Web. F equals P over A. 50 KSI equals P. Stress, we're using the 81. That's the largest force of any kind, tension or compression. Looking for the area. really hates where I write decimal points, I'm telling you. Area for the web, not to fail due to stress, is 1.634 square inches. It could be based. Oh, where did it paste it? Right there. Boom. The force used for buckling is the largest force in compression, that is 50.4 kips. That equals pi squared, 29,000 to 0 kips per square inch times the moment of inertia divided by 1 times 10 feet, 120 inches squared. I got a much smaller number than I did up above, but maybe that makes sense. But it's like, what? Panic, panic, panic. Well, we'll go back and we'll look. We'll check. 254 inches to the fourth. Well, let's see. Up here I had 126 kips. I had twice as much force, and I had 16 feet, twice as much length. Okay, yeah, so twice as much length is times 4, twice as much force is times 2 again, so that's times 8. So 2 times 8 is 16. So yeah, okay, we're cool. Now it's back to the chart. If I had done this in timber, I just used, the moment of inertia for a rectangle. But it's in buckling, so you want to use the weak way. But you've got 2 dimensions here, so you're going to well, maybe it's a 2 by something. And you say, well, that's B, so this is D. And then you just use, it's going to be D times 2 cubed over 12. And then you just solve for D. Okay, what do I got? I need, again, on the chord, I like the double angles, just because of the way the trusses go together, just because of what I've seen in the field. I need an area of 2.52. Two point 2.7. Okay, so this is 2.7, this is 2.52. 2.8 up there. Now what I'm looking at is 2.8 is close, and this weighs 9.8 pounds. Don't know what I was saying. Plates. Got a variety of different sizes and a variety of different weights. It looks like IX is always going to be the smaller. So 2.88. I'm looking at the wrong number. Oh, no, area. Never mind the I's. Still looking at 2.52 square inches. So 2.88 does it at 9.8 pounds. 2.9 does it, 10 pounds. 2.7 does it at 9.4 pounds. Aha! Getting lighter and getting smaller. I like smaller. 2.3 is a little too small. And then we're getting into the big LLBs. Okay, so this is a cord. So I'm going to want to, I'm going to want a gap to put a little plate in. And I like the 3/8. That way I can buy the same plate stock. Doesn't matter because it's going to be the fabricators fabricating it. They've got everything they need. So we'll use we'll propose for stress purposes, a 2x2 by 3/8 by 3/8. Gosh. 2x2 by 3/8 by 3/8 with an area of 2x2 by, that was 2.74, 2.74. And not to run into buckling trouble, 17.62 inches to the fourth. 2x2 by 3/8 by 3/8 gets us nothing in the moment of inertia category. This is where we start to get into real structuresy things happening, where stress usually isn't the problem, and it's going to be buckling. So let's crank it up. There's a 20. 17.3. Let's not play games. 17.9. That's the 3/4. I think I'd like to stick with the 3/8 plate. Oh, we got to go with the weak one. IX. Never mind any of that. 17.5. Well, since we don't have a safety factor, 17.5 is, I can't mess around with that. So I better go with the 5 by 5 by 7/16 by 3/8. 2L 5 by 5 by 7/16 by 3/8. That has an I of, it was big, where did it go? IX of 20. IX of 20, area of 8.4. So that's what I'll use for the top and bottom chord. And for the web, areas 2 by 2 by 8 gives me not 1.4, 1.8. I can go with a 2 by 2 by 1/4 by 3/8. WL 2 by 2 by 1/4 by 3/8. Area equal 2 by 2 by 1/4 by 3/8. Area 1.89. 0.89. I need a moment of inertia of 2.54. Not getting it from this. 2.46, almost close. And again, without the safety factor, I'm not going to be playing fast and loose. We'll take the IX of 3.0. We'll stick with the 3/8 gap. 3 by 3 by 5/16 by 3/8. Double L, 3 by... Oh, this is the web. Yeah. Use the singles. Yeah, sure, let's go with the singles. Wrong way. Here we go, here's the singles. What can we get for an area for 1.634? Area. 3 by 3 by 5/16. Oh no, not for the chord. Chord wants to be the double. Area. This is the web. This brings to mind a saying of mine. An awful lot of doing structures is about bookkeeping, just trying to keep track of what it is you're doing and what you're looking at. So, the web, single angle, 1.89. I can do the 3.5 by 3. Oh, it's an L3. No, it's an L 3.5 by 3 by 16. Oh, yeah, right. They write these differently than they do the double angles. And I always get confused when I switch between the sections. So I need 1.95. That'll do 1.63. This will do it. Anything bigger down here? 3. This is the big truss. Yeah, but it's the web. I was just thinking, maybe for the big truss I wanted something big, physically large. But, well, I got the 5, so the web wants to be a little lighter. The 2 by 2 doubles might be good. I'm just thinking for aesthetics, 2.11, 1.09, 1.78. Let's do that. Let's do the 3 by 3 by 5/16. For the area, 3 by 3. This is a single angle, 3 by 3 by 5/16 with an area of 1.78. And for a moment of inertia, I need 2.54. This isn't getting it to me, so we go up 2.54. Oh, IY is weak. 2.86, 2.86. That weighs 8 pounds. That's a hideous disaster. Yeah, I don't want to go too big, just because compared to the 5s, I want something larger, or smaller. So, it's like I've got, my webs are big, or chords are big, and then I want my webs to be a little smaller. 2.54 on the weak axis. So this is good. That's close, but no cigars. This is no cigars. That's the first one that'll give me the 2.54. Okay. So that is a single L 3.5 by 3.5 by 3/8 with an I, X and IY of 2.86 and an area of 2.5, which is big enough. So that's what I'll use for those. And now all we have to do is the column, because these are the member sizes for the large truss. And again, I'm only doing top and bottom chord are going to be the same. And then the stuff in the web is going to be the same. Based on the worst case of each category. I've got a column to solve. You just throw this in for completeness. If you're doing arches, maybe your arches reach all the way to the ground and you don't have to do the columns. And you say, well, come see me and maybe I'll make you do the footings. That'd be interesting. I need my numbers off AutoCAD. Here we go. I think it's a 5-foot square, but that's not necessarily true. I know it's 60 feet long. Feet. I know it has 50.4 tips on it. So, for stress, F equal P over A, I'm going to use a hollow square section, which will be 50 KSI steel. And it has to hold 50.4 tips, so the area is going to be the tiniest hair over 1 square inch. Area equals 50.4 divided by 50 equals 50.4 divided by 50, 1.008 square inches. And for buckling, $50.4 tips equals pi squared 29.123 times I over the column. If the whole unit moves, if the whole roof starts moving sideways, sure, the column can go with it. But that's not really what we're talking about with bending. Sorry, with buckling. With buckling, we're saying here's a column, and there's a roof. There's the ground. So how are we going to attach this? Well, maybe we'll attach it with a pin at the bottom, and at the top it'll certainly be some kind of pin. And if this wants to buckle, well, the roof and the other columns will keep this in place. This won't move sideways or anything. And it's not like they're all going to suddenly try to buckle at the same time in exactly the same direction and throw the roof in the exactly same direction. No, so the roof, just by its inertia and by the other columns, are going to help keep the top of this column in place. So this is a pin pinned, unless maybe my column size goes insane and I'm like, well, maybe if I put it into the ground and make a fixed connection out of it to get a, to get a K of 0.7. That'll save me a little, but I'll go with K equals 1 for now. And a pin connection. So 60 feet times 12 inches per foot squared. times 12 equals squared times 50.4 divided by pi squared divided by 29,123 equals, I need an I of 91.3 inches to the fourth. So, square HSS, where'd my cursor go? There it is. It's just a hollow steel section, a hollow steel section, and you can get those pretty big. So I'm thinking we might be able to find one suitable to be the columns here. An area of 1 square inch should be really easy to meet. Way down at the bottom of the table, probably. Yeah, so like 2 by 3 by skinny. I'm kind of just going to say don't care. Confirm. 91.3. Yeah, we're getting up here. We're getting a little larger. IX and IY are going to be the same because these are square. So what did I say that was? Not okay. Oh yeah, 5 feet, right? So 10 inches. I can get a 20, 18, and that'll get me an I of 900. I mean, basically I can make this whatever I want. That's just 105. That's a 10. So how about if I just say, I'm going to go with the HSS 10 by 0.375. That way everything can be a 3/8, right? Not that it matters. It's just poetic. With an I of 123 and an area of, where did it go? 10 by 10 by 3/7 area is 10.6. So these are both, this one's only a little bigger than it needs to be at 123, but I like the 10 inch. You know, okay, well, we'll say, you know, okay, required will be good to get 1 inch, just the tiniest hair over. I need an HSS 2.375, HSS 2.375 by area of the 1.2, 0.188, 0.188. And for this required, oh, where can I get 91? There's 100. That weighs 43 pounds. 93, that weighs 31 pounds. I might drop down and use that anyways. Because there's no big difference, it's just a weirder looking number. The 10 by 10 by 3/8 was 38 pounds. This is 31 pounds. Yeah, steel is money. We'll use the HSS. 9 5/8 by 0.31. What's 312? Some number of 16ths to 30 seconds with an area of 8.53. Yeah, that's way too big, but that happens. Don't care. And IX of 93. So that's what I use for my column. I already have a pretty picture somewhere. It's nice to have a pretty picture just because when you look at the, there's my plan. And like, what's that a plan of? That could be a plan of like anything. Well, the elevations kind of help. Yeah, but you know what really kind of helps? Something pretty. Don't you bother making it too fancy if you don't have time or effort or maybe even skills yet, because some of you might be in your first semester just coming here from who knows where. But try to get something up that looks a little reasonable. That just, so a person coming in and seeing these plans, elevations, whatever, has an idea of how they're supposed to go together. And aside from that, all I got to do is write up those equations and make them pretty. I was in the wrong place there. Stylize, color pencil. That's actually, is that broken? Or I think I found a bug. Okay, so the last step is put it all together and send it off. That is, aside from making it pretty, that's a structure project. I'll get this wrapped up, put everything online, and let you know.